Good morning. I'm Bruce Muschlitz, and I'm the 61850 PRP and merging unit expert at NovaTech. First of all, what are we going to talk about? We're going to start talking about 61850. Why would people want to use 61850? What does it bring to the users? Users need to have some structure to their data. Having unstructured data is a recipe for disaster. You want to have your objects have specific names and specific semantics so that you know what objects you're talking about. If you want to look at some objects in a device, you should have an easy way of deciding what objects are available in that device, either offline or online. Offline, sorry, thank you. Offline 61850 offers you the XML based language called System Configuration Language, which allows you to look at a device before you even purchase it or buy it or install it. You can see what objects you've got and what objects you can use. 61850 also brings a system engineering process to your system. Even if you don't use 61850 for everything else, the 61850 engineering process is extremely valuable to use. 61850 also brings a way of automatically pushing data from one device to many devices through two mechanisms. One is called goose and one is called sampled values. The difference between the two is very simple. The goose is asynchronous. When something happens, when an event happens, the goose is sent from the source device to all the destination devices, whereas as in sampled values, they're periodically sent. There's a definite period for these sampled values. 61850 also offers a large wealth of maintenance and debug features so that when you're doing a commissioning of a system, you can easily figure out what's communicating, what's not communicating, which objects are moving from place to place, which ones aren't getting to their destination. 61850 also has built-in security through the 62351 suite of standards. That's IEC 62351. So how is it different from traditional protocols such as DNP or Modbus for that matter? In 61850, the normal transmission method over the Ethernet is to push the data only. There is very little in 61850 where you actually do polling. In DNP, the typical mechanism is to poll every 4 seconds, so your data is stale by 4 seconds at all time. In 61850, the data in all the devices that need the information is instantaneously available. Instantaneously means at the millisecond level. So milliseconds after an event occurs, all the devices have all the information. Again, 61850 has named objects instead of numeric indices. In DNP and Modbus, you've got point number 5. What's point number 5? It could be a watt value, it could be a volt value. What's the scaling of it? Is it in megawatts? Is it in kilovolts? And then other parameters of it. What's the quality of it, for example? Is it good, bad? Has the device detected that it's out of range, for example? Also, 61850 offers the ability to have the objects, the named objects, travel all the way from the source of information to their final destination. There is no intermediate translation as you have in DNP. I'll give you an example. If you've got two DNP devices, they typically get put into a data concentrator, and in the data concentrator you remap the points into something else. Now somebody's got to keep track of all this remapping. When the points finally get to their final destination, you have to unmap them and put them back into areas so that they know where they came from. 61850, you don't have that problem because all the objects are named and the names are unique within your system for every object. 61850 also expresses all the values in primary units. No more need to worry about scaling. Is this in tens of kilovolts? Where's the decimal point? No question about that. All this information is available when you look at the device over the wire. Very simple. 61850 has gone through a couple of transitions. It's gone from UCA2, which was initially started by AEP back in 1995. Then went through a transition where it became internationally standardized as IEC 61850 in 2005. In 2010, they recognized that there were some features that were missing and some misunderstandings in the standard, so they reissued the standard as Edition 2. We're currently working on reissuing that standard again as Edition 2.1, which will be a remapping of the standard from paper documents to UML-based documents. The key to doing it in UML is the consistency among the objects and concepts within 61850. All of it will be standardized in UML. UML will be able to do cross checks across all parts of the standard, and the paper documents that you get from PDFs will be generated from the UML information directly. There's a program that they have that just takes the UML model and turns it basically back into the paper model. Soon after that, we'll be going to edition 3, which we're currently working on in the IEC group. I'm a member of the TC57 Working Group 10 that's working on the maintenance of 61850. Been in that group for many, many years. So edition 1, again, was a good start, and it's a very good standard. However, there were some problems that were found. Obviously, you've got a 1,500-page standard. You're not going to make it perfect the first time. So as experience showed that there were some holes missing, some misunderstandings, some ambiguities in the standard. They were verified and eventually turned into edition 2. The edition 2 had added a lot of testing features, made it much easier to use. But again, because the standard had become a little bit more complex and a little bit more, a lot more to it, they found some of the new features they put in had some other issues. So they essentially did a quick turn, and they're trying to release this edition 2.1 now. They expect to have that finished in 2016. The different versions were designed to be compatible with one another, and there is a roadmap of telling you how to go from an edition 1 system and, for example, add edition 2 devices. I will tell you that the configuration of those editions, if you mix them, can become difficult to do. It is possible to do, but it can be difficult. If you're starting from scratch, my recommendation right now is to use edition 2. It's much better than edition 1, has much better testing features, is much more well-defined. But for a brownfield where you've already got existing edition 1 devices, you can add edition 2 devices. It just becomes a little bit more interesting. So how do you start with 61850? You've got a legacy system out there, and your boss says, we want to put 61850 in. What do? Well, there's a couple of baby steps you can handle. Now, the first baby step is putting Goose on top of other protocols. I know this sounds kind of strange, but GE had been doing this for years with the UR relays. They sold DNP devices that had Goose built into them, and the GE relays could talk to one another. And when the customers asked, how does all that work, GE would just respond, it's magic. Well, the magic part was actually putting 61850 into their box and not telling anybody about it. Okay, so you can actually do this yourself. Put the Goose on there, and what the Goose will add to your system is it will remove the device-to-device wiring. So if you look at a substation, for example, you'll see a lot of wiring that wires box A to box B to box C, box A to box C, and it becomes a real nightmare when you've got 10 devices. Then you've got 10 times 9, 90 wires that you've got to potentially link between these devices, or even more. What the Goose allows you to do is you have one sender and all the receivers receive it at the same time. Very good application to put Goose in. Another application that they can start with 61850 is to go to do a sample value system. Now, the sample value system in 61850 typically uses a device called a merging unit, and I'll get into that a little bit later. But what it allows you to do is to digitize the samples at the source and then use those digital samples elsewhere. And those digital samples, again, are broadcasted out to all the devices that need it. Okay, very good, very interesting concept here, and there's some very, very good reasons to do this in terms of physics. So, if you're, again, as I said before, if you're just starting out, please use edition 2. Don't go to edition 1, okay? Find the devices that implement edition 2. They are much better to use. Parallel redundancy protocol. This is used for redundancy on the communication links. There's 2 sets of redundancy protocols that are specified by the IEC, both under the IEC 62439-3. One is called Parallel Redundancy Protocol, and one is called HSR, and I'll get into that a little bit later, the High-Speed Seamless Redundancy Protocol. What PRP does is it duplicates all of the network, the network switches into 2 separate groups and transmits the data on both of the groups concurrently. On the other side of the switches, you have your receiver, and basically what the receiver does is it takes the first message it gets and uses that and throws the other one away. Very simple. The key to this is that it's seamless. If you break a connection in your communication system, you lose 0 packets, exactly 0. In a normal office type environment with switches, you have this protocol called RSTP, Rapid Spanning Tree Protocol. During the reconnection process, when it reconnects, that can take up to 50 milliseconds. In an office environment, no one will ever notice their email didn't get through in 50 milliseconds. In a substation or a real-time automation system, that's death. You really can't have that. You need something that actually has zero packet loss. So they call that the bumpless redundancy system. So again, I've described that that is essentially sent out twice. Let's see if I can get this off of here. Sent out twice. The first one who receives it wins, throws the other one away. There's devices called red boxes that can convert from normal Ethernet into this parallel redundancy protocol. Okay, they're not red; they're redundancy boxes. They're usually black. Okay, some people paint them red just so. No, that's a red box. So compared to Rapid Spanning Tree Protocol, no data loss. There is no tens of milliseconds. It's zero recovery time. The high-speed seamless redundancy is another system that can be used, and basically it takes all the switching equipment and puts it into the end devices. So basically your switches are in the end devices, and it puts them into a ring, and I'll show that to you later. The problem with HSR is it's limited in size. Once you get beyond about a half a dozen devices, you'll find out that the links get clogged up, and I'll show you why that happens. Each device must support the HSR because basically the HSR has the redundancy part built into it, and they also have HSR versions of these redundancy boxes used to adapt non-HSR equipment. So this shows you how a PRP system works. So imagine this switch here is actually an entire switching infrastructure. Okay, the idea is you keep them completely separate. You take each of these infrastructures, power them off their own power supply. You take each of these wires, you make sure they're physically separated. So if we can see here, we'll get a source of the information coming from here. So the source of information goes comes out of both of these ports, goes into the switching infrastructure. Switching infrastructures gets into the destination, and the first one that gets there wins. For example, LAN A could win. If you break LAN A, then LAN B is going to be the first one in. The system doesn't care. The first one in there wins, and there's absolutely no packet loss at all. The key is that this thing has to dump the redundant message, but it knows this by sequence numbers. Now, you can have devices called singly attached nodes. You just take regular Ethernet stuff and you put it into your network. The system will recognize the fact that this is a single one. You have no more redundancy, but there's no extra stuff you need to do. The other thing you can do is you can put your red boxes in, which will convert your regular Ethernet into this dual port Ethernet. So this one shows three normal Ethernet ports and one of the PRP ports, and it does the conversion for you. So this one sends it out. If this part of the network dies, again, this will get through. This one will get here through the blue line, and everything will be fine. So again, you can use a red box to get your full redundancy, or you can simply attach your normal Ethernet devices. You really don't have to put new ones in. With normal Ethernet devices, if you don't use a red box, remember, you've lost that redundancy. HSR. The HSR basically connects each of the devices into a ring. So for example, normally, this is the normal flow of traffic, okay, around the ring. So the sender device puts things onto the network. When the message gets back to the sender, he recognizes that he was the one who sent it out, and he drops the packet. If he wasn't the one that sent it out, he passes it through the next one, or uses the packet himself. The data flows in both directions on these. So if you lose one of these lines, if the traffic was normally going clockwise, okay, and it went from here to there, and you lost this link, the data would simply travel counterclockwise and get to the same location. The only difference you'll find is that there's a slight delay. Now, if you look closely, what you'll notice is that when this sender puts information onto the network, he puts in, let's say he puts in 10 megabits of data into the network. This one puts 10 megabits of data into the network. This link now has 20 megabits of data. This one adds another 10, this link's got 30. This one adds another 10, you got 40. You can see that this is very much bandwidth limited because each of the links has to carry this sum total of all the data. Whereas in PRP, there is no limitation. Okay? You can put in thousands of devices, whereas this is limited to about 5, 6, 7 But once you get beyond that, you really have to start worrying about bandwidth calculations. So we do have this limit compared to PRP. Process bus, the merging units. As I said before, the idea is to digitize the data at the source. So out in your station yard, you've got your CT and VTs that are hooked onto the primary equipment. And the typical way to do it is to take all those CT VTs, run all parallel copper wires, some of them very thick, 10 gauge, 8 gauge wires, run them all back to the control house, put them into multiple barrier strips, and run them to all the devices on the CTs. You've got to make sure all the devices are in series, and these lengths can get quite long. What's wrong with long wires on a CT? You have more impedance. The higher the impedance the higher the burden on the CT, the higher the chance of CT saturation. CT saturation is very bad. There's also the chance, because you run it to all the devices within your substation, one of those CT wires can get loose and break. And when that happens, there's a term we use in the engineering industry called explosion. Okay, very, very bad things happen. You will destroy something. If you are lucky, you'll only destroy one device, but that device will be turned into a piece of charcoal. I guarantee that. So in the merging, and again, you digitize it at one source. It's received by all the devices that are interested in the data. Only the devices interested in the data will actually see it. You have no more long runs of bulky cables. You have no more worries about opening your CT loop or having your dangerous 120 volt signals in your control house. Working with 120 volt signals, I know people say it's only 120, doesn't hurt that much. This is what we call lethal voltages. You really don't want that. So also in process bus, in addition to sending the periodic data that I described to the merging units, there's aperiodic data that can be sent. In Goose, with the what you can do is you can replace all the dedicated wiring that's going from device to device with the Goose. Again, the sender puts the information on the Ethernet, and then all the devices that are attached to the same LAN on the Ethernet are able to retrieve that information simultaneously. Okay, it's kind of like magic. The information that can be put into a Goose, it can be analog, binary, structured information. You can essentially put anything you want into a Goose. So basically, when a sender recognizes that something has happened, he will immediately send a Goose message out to all the interested devices, and the interested devices will be updated with that information within milliseconds. I have here 4 milliseconds. Now, the really interesting part of Goose is that it's faster to use this Goose to transmit the stuff over a communication link than it is to use a straight copper wire. And everyone challenges me on that one. How can it be faster to encode, decode, communication processing, putting it on wire, taking it off, all of that? How can that possibly be faster? In a real system, what you have on the output of your box, if it's a wired connection, is a mechanical relay. That mechanical relay takes approximately 4 milliseconds to activate on its own. On the other side of that, you have an optocoupler input, and the optocoupler input has a debound circuit on it, which typically takes about 8 milliseconds to settle down. So between the two of them, with a piece of copper, you get an 8 to 12 millisecond delay, just because it's a piece of copper, compared to the 4 millisecond you get if you put it over transmission media. Now, the next thing you're going to ask is, isn't this going to take up a lot of bandwidth? What happens if multiple messages want to get across the media at the same time? It turns out that these Goose messages are actually quite small, and they really consume a very small amount of bandwidth. The other very, very cool part of Goose is that it has a built-in keep alive system, so that if the sender stops sending the messages, the receiver can know that that sender is dead within a few seconds. And when the receiver detects that the sender is dead, it can go into a backup mode. For example, it knows that the sender's not going to be sending information. It's not like a copper connection where the only way you know that the connection's been lost is when you need to trip that breaker. Whoops, sorry, lost the connection, can't trip the breaker. This you know within a few seconds that the connection has been lost or the sending unit has gone down. Very, very important feature of Goose. Just for that, it's probably a good idea to put this in. For distributed fault recorder applications, the typical way to do this is to have a bunch of boxes. Each of these boxes is attached to multiples of CTs and VTs, and they're independently collecting data, and someone on the other side's got to be able to pull the information out. In 61850, we can set up a system where each of the signals is digitized at the source, sent to a single destination, which can then go and collect all the information, and then tell an upstream device that something has happened. It's time to pull the oscillographic information out. What kind of information would you want to have in a fault recorder? It's not just faults. It could be disturbances. I'll give an example. Let's say that you have a sag in your voltage. There's a reason for that sag, and you really want to know why that sag occurred. So this system could collect the information. This could decide that a sag had occurred on phase A, collect the information, determine what happened on phase A. Maybe there was a fault on another feeder in the system, and it depressed the bus voltage, and that's what caused the sag. So you can use this to analyze information like that. The standards that are used in 61850. Remember, 61850 is a collection of standards. They didn't really invent very much on their own. So they used a bunch of existing ones. For example, for time synchronization, they used the RFC 2030 and RFC 4330, which is Simple Network Time Protocol. That's been in use since 1983. Very well thought out and very well standardized. They do have security in here for time distribution. We also, in 61850, use 1588, the Precision Time Protocol, PTP, and the IC people have come up with a profile of the 1588 that specifically is used for power systems. Okay, so remember, a profile is simply a subset of 1588. So it is 1588. It just nails down some of the optional parameters so that all the devices can truly be plug and play. 61850 is also based for its client-server access on ISO IEC 9506 Part 1 and 9506 Part 2. I always forget which one they are. One is the services, one is the protocol. Essentially, you have to buy both to get everything out of it. But this is the basic messaging system that's used inside of 61850 that uses named objects. We also use the standard TCP/IP suite, RFC 791, 793. These standards, if you know the standard numbers, they're very low. These have been out there since 1982, 81. They're really old standards. Everybody uses. That's why they're so popular. It works for everybody. So all of this stuff just hangs off a standard network, coexists with all the other protocols you've got, including things like DNP, IP, or Modbus TCP. For Parallel Redundancy Protocol, the standard is IEC 62439-3. Also, the HSRs is in the same specification. These specifications were derived for industrial networks. They are derived for absolutely zero packet loss. If you think about an industrial process where, for example, a printing press for a newspaper, there's some very, very strict timings you got to put in there to make sure your colors actually line up on the paper, for example. Very, very strict processing, very strict timing requirements. For the process bus, we use the recommendation from UCA IUG called 92LE, which is a profile of 61859-2. It is 9-2, but we're again nailing down the parameters of there, so it becomes plug and play. For example, 9-2 says you can send samples out at any rate. 9-2LE tells you that rate for 60 hertz systems is going to be 4.8 kilohertz. For a 50 hertz system, they tell you it's going to be 4 kilohertz. There's also a new standard for process bus coming out, 61869-9, which came out of the instrument transformer group. So they're probably going to take over the verification of this. One of the things they added here on the merging unit is to come up with transient information. If you're familiar with the transient information that happens in synchrophasers, okay, in synchrophasers they have the same kind of issue when a transient occurs. All the filtering algorithms can get out of whack. This one specifies essentially all the filtering algorithms, so all the devices will give you the same information. So I have a comparison here of 61850 to DNP. Let's start with the DNP side. On a typical DNP system, you've got a box called a data collection box. We can call this an Orion if you want. So the Orion has two parts to it. It's got the master side and the slave side. The master side polls all of these devices, and all of these devices have duplicate inputs. For example, the meter and the relays both need the same set of CTs and VTs. You've got a serial wire the CTs, you've got a parallel wire the VTs, and the relay independently talks to the breaker. Nothing else can talk to that breaker. For example, the meter can't have any access to that breaker. He's not connected to it. On the slave, once it collects all that data and does its operations, it then passes it over to the slave part to allow you to send that back to your EMS system or your central controller. In 61850, it's actually quite a bit simpler. You've got an Ethernet switch, okay, and the Ethernet switch just has generalized ports. Some of those generalized ports go out to the EMS system. Other generalized ports just connect to your devices, your breaker, your relay, and your meter. So if you look at, and the data collection is done with the merging unit. So if the meter needs information, he simply goes and subscribes the information coming out of the merging unit, and he gets all of this data. No more double wiring. The relay needs the information. He gets the data. No more double wiring. If the meter wants to monitor the breaker, he does that through the Ethernet fabric. He doesn't have to have a direct connection to it. Same with the relay. The relay will probably be doing the tripping. The meter is probably going to do the status verification along with the relay, or it could, for example, do some verifications on how long it takes to travel, how long the overload occurred. So the meter can actually see overloads occurring, just like the relay can. Say, aha, I've seen an overload, and it has taken me 12 milliseconds to clear that fault. Whereas the relay may have a different idea because he saw the fault a little bit later because of his filtering algorithms. Also, you can simply hang off the system controllers that you have, for example, an Orion, or you can hang off an HMI. Again, that could be another Orion. But the key is that all these devices share all the information without explicit links. The explicit wiring is all gone. See all this wiring? All that stuff's gone. You just have this wiring, and all the other information is traveling through the Ethernet. So that's it. I had a paper yesterday called Distributed Data Recorders, Killer App for 61850, where I tried to explain in more detail how distributed data recorders work and how it reduces the amount of additional wiring that you need. It was a good paper. The paper and the presentation should both be on the Penwell site, so you can retrieve that information. And here's my contact information. And I thank you. And I thank you. And I thank you.